So today's set of videos is going to focus on this fundamental problem in computer science called the P versus NP problem. But before we get there, we have to make some definitions, and we have to define a class of problems or a type of problem called an NP complete problem. So very quickly, let's recap kind of where we have been. Last time in the last set of videos, I defined a couple classes of problems, right? So one of the classes of problems I defined was the class P. And so we can think of class P as the class of decision problems. And a decision problem, remember, is a problem that has a yes or a no answer. So we're going to be very strict about defining these as decision problems from here on out. So the P is the class of decision problems that can be solved with a polynomial time algorithm. So if I give you an instance of a problem in class P, then there is some polynomial function of the size of that problem that describes the running time or the execution count, if you want, of an algorithm that solves the problem. All right, so for example, here we have, so this is the class of decision problems with polynomial time algorithms. And I'm going to say for solving from scratch. So if I give you an instance of a problem in P, I don't have to tell you anything else than the instance itself for you to be able to solve that problem with a polynomial time algorithm. So for example, we talked about this array search problem where I give you an array with n elements and a threshold, and I ask, does there exist an element in the array above this threshold? And clearly you can solve this problem in polynomial time by walking down the array and just looking at each element in the array to see if there's something larger than that threshold. Right? It can be solved in linear time, thus it has a polynomial time algorithm. And I don't have to tell you any extra information for you to be able to solve that problem. So another class of problems, another important class, is called the class NP. And so let's call this the class of decision problems, I'll abbreviate a bit, with polynomial time algorithms for verifying correct solutions. Now I'm glossing over some of the details when I describe it that way. But that's for our purposes, that'll suffice here. The idea with an NP problem is that if I give you a problem and then I give you a solution to that problem, or maybe you could even think of this as kind of a candidate solution to this problem, you can check that is a solution to the problem in polynomial time. So you can't necessarily, and I should emphasize necessarily, you can't necessarily start with an instance and then solve it in polynomial time. But if you start with an instance plus an additional piece of information called a proof, or we usually think of it as a solution to the problem, then you can verify that proof or you can verify that solution in polynomial time. So the class of decision problems with polynomial time algorithms for verifying correct solutions. And I'm saying correct solutions, and anybody who's hardcore into CS theory is gonna grouse about this a little bit. But the idea is, if I give you a problem and a proof that it's a yes, that instance is a yes instance, you can check to see whether it is actually a yes instance or whether I'm lying in polynomial time. Okay, so there are some subtle details here that I am glossing over, and I just want to leave that caveat out there for your consumption. So for verifying correct solutions, and I'll say correct solutions / proofs, but not necessarily for solving from scratch. So here's our fact. Here's the fact that relates these two problems, is that P is a subset of NP. And there's a couple different ways of thinking about this. For our purposes, it's going to be really useful to think of it in terms of how hard these problems are to solve. So if I say P is a subset of NP, one of the ways of explaining what that means is I can say a problem in P is no harder to solve than a problem in NP. Or if you want to be more verbose about it, you can say, the class P is the class of decision problems that I can solve from scratch fast. And the class NP is the class of decision problems whose correct solutions I can verify fast. And so what this subset relationship means is that it's no harder to solve a problem from scratch fast than it is to check a correct solution fast. Okay? And so we can essentially use this inclusion here, this subset relationship, to say that problems in P are no harder to solve than problems in NP. Or problems in NP are at least as hard to solve as problems in P. So you can kind of think of this as problems in P are no harder than problems in NP. In the CS theory world, a lot of times what people say is that the class NP is more powerful than the class P. And this is, in terms of the linguistics of this, I won't complain too loud, but it rings weird to say that a class of problems is more powerful than another class of problems. But what this kind of harkens to is this idea that when we define a class of problems, we often define it with reference to some kind of a computational machine or a computer type or something like that could solve problems like that. And so what we're saying when we say that NP is more powerful than P is we're saying that a machine which can solve NP problems is more powerful than a machine, or I should say at least as powerful as a machine that can solve only P problems. So we kind of imagine that there's this device that we can take an instance of an NP problem, stick it in there, and then that device can give us an answer, right? That device is more powerful, or I should say at least as powerful as a device that can take an instance of P, of a P problem and solve it, right? So there's a bunch of different ways of describing this. A lot of times in this lecture, I'm going to use the word harder, right? So I'm just going to say this subset you can think of as a less than or equal to, right? So almost think of this as a less than or equal to, right? And it's even shaped like a less than or equal to, right? The problems in P are their hardness is less than or equal to the hardness of problems in NP, is one of the ways of thinking about kind of what this means. So notice I've been very careful of to focus on this less than or equal piece, right? All we know for sure, just so far, is that we have this fact that problems in P are no harder than problems in NP. What we don't know, at least so far in this course, is whether or not problems in P are strictly easier than problems in P. In NP. So the question we'll be addressing today is, we know that there's this less than or equal to, but are problems in P strictly easier than problems in NP? Are probs in P strictly easier than, and here I'm going to be a bit precise, I'm going to say than the hardest problems in NP. Okay, so last time I drew this Venn diagram, the Venn diagram looked like this, where I have P as a small set inside NP. Okay, so this Venn diagram, which shows a space in between P and NP, right, shows these problems here. This Venn diagram would represent an answer of yes to the question that I just asked. So if the answer to this question is yes, then the relationship between P and NP is one of proper inclusion, proper inclusion. And in other words, the set P would be a proper subset of the set NP, which means that there are things in NP that are not in P. All right, so this Venn diagram means that there exist, if this Venn diagram is the state of the universe, right, is the universe we live in, this Venn diagram would mean that there exist problems whose correct solutions can be checked fast, but that we cannot derive correct solutions to from scratch fast. Okay, so if there is a dot there that is in NP but not in P, that means that there's this strictly easier than relationship between P and NP. But an answer of no to this question, right, would look like this. It would look like both sets are the same, right? It would say P equals NP. And, if I tried to draw this as a Venn diagram, I would draw, there's my set NP, and then I'll just draw another circle here. And that there's my set P, right? They exactly overlap on one another. And this would mean that it's always, that if I can verify a problem fast, then I can also solve that problem fast. So we'll talk at length about this today, but it turns out that it is generally believed that this is the true state of the world. So believed that P does not equal NP. And we tend to kind of expect that this is the true state of the world. However, when I say believe, I'm being serious, right? I'm being serious in a big picture research community sense. That to date, and what's the current date, right? November 12th, 2020. To date, nobody has actually proved for sure that that's the state of the universe. So it's actually possible that the Venn diagram on the right is correct, and we'll talk about what the implications of that would be as the day goes on. And that would actually be quite an interesting thing to be true if the Venn diagram on the right is correct. But you'll often see in the computer science literature talk about the P versus NP problem, and this is what that question is talking about. So the following videos are all going to discuss what we mean by this, what are the implications of one versus the other, and how do we even develop language to talk about this problem in the first place.